Every loaf of Wonder Bread, and most other American breads as well, starts in a wheat field. 100,000 square miles of wheat are harvested every year in the U.S., an area equal to the entire state of Colorado. Every grain of wheat has three elements: a protective outer layer called bran, which contains vitamins and fiber. The germ, which is the embryo of a new wheat plant, is made up of oils and minerals. And the endosperm, which provides the nutrients for a new plant, mostly protein and starch. White flour is pure starchy endosperm. Separating that out has been the goal of every flour mill since the beginning days of bread making. One of the most modern mills in America is the Hal Ross Mill at Kansas State University in Manhattan, Kansas. Here, students and professors experiment with the latest in milling technology in a full-scale functioning flour mill.
This wheat that we're going to mill today is Hard Red Winter, and it gets its name because the outside of the berry is reddish brown and the inside of the berry is hard and vitreous, and so about 75% of the inside part of that kernel we can turn into white flour. The rest of it ends up in a byproduct, either as feed or maybe as bran in a breakfast cereal or a bran muffin or something like that.
Today's mills are an elaborate labyrinth of pressurized tubes and equipment that move the grain particles from floor to floor. The grinding operation begins on the first floor, where stainless steel rollers do the work of the ancient millstones.
Whole kernels are coming down, being fed in to what we call a double high roller mill. We've got two sets of big steel rolls, one on top of the other, that this product is passing through to be broken apart to try to remove these chunks of endosperm from the kernel. We've got here a 5-story building. We've got equipment spread across all floors. As we lift the particles by negative air up to the top floor and then drop it into a sifter.
Inside the vibrating sifter is a series of screens of smaller and smaller apertures. The flakes of bran and the oily wheat germ particles are sifted out at the top levels. The smaller powdery particles of endosperm fall through to the bottom.
On the large size, we have big bran flakes, and clear over on this side, we've got flour. So out of that mixture, we've separated the finest particles for flour from the largest. In the middle, we've got some particles that still need to be processed.
Optic sensors isolate and remove defective grains of wheat. High-speed impact machines destroy any insect eggs or parts. And flour streams with distinct quality features. Infinite variety of flour mixes.
Here we've got the ability to take samples from each of the different flour streams in the mill.
Knowing how to mix the flour streams to get the best quality white flour requires more than just a good eye. Across the Kansas State campus in the Bakery Science Laboratory, scientists have devised dozens of tests to check the quality of the flour and the bread that it bakes. The texture analyzer measures the firmness of baked bread. A machine called the Extensograph tests how well the flour responds to kneading and mixing. And this device, the Alveograph, tests how well dough will retain the carbon dioxide air bubbles created by the yeast by testing the quality of one of bread's key and unique components, gluten.
Wheat contains a protein called gluten protein. It's the only cereal grain that contains gluten. When it develops, gluten forms into a cohesive mass that is able to retain gas. So when you're making bread, the yeast is fermenting, is producing gas. This gluten protein can hold that gas inside the dough. That's why your dough can raise to give you a nice expanded loaf of bread.
This ability to retain gases and to rise is unique to wheat flour and was recorded by the Egyptians around 5000 BC.
It was completely luck. Somebody was having a porridge or a gruel that they left out too long, prehistoric, Paleolithic times, and wild yeast got in there and they left a little more and they noticed that it started bubbling, and when they baked it, it wasn't dense and hard, it was light and expanded.
They had unlocked the power of the yeast spores that occur naturally on grain and in the air. For the next 7,000 years, bakers learned to hold back a portion of their fermented dough, called the mother dough, to mix with additional flour and water, creating new batches of yeasted dough. But the actual science behind leavening bread remained a mystery until 1859, when Louis Pasteur discovered that yeast was a single-cell living organism. With that knowledge, scientists soon learned how to grow yeast separate from the dough. This sparked a revolution in bread production. At the Fleischmann's yeast factories in Memphis, Tennessee and Montreal, Canada, new life is created every second of the day. Selected yeast microbes are mixed into vats of yeast's favorite food, warm, unrefined molasses, a byproduct of sugar production that would otherwise go to waste if it weren't perfect for developing bread yeast. This fermentation process is very similar to brewing beer. The difference is, once the 36-hour fermentation is complete, Fleischmann's throws out the alcohol and keeps the yeast. Yeast responds to the slightest changes in environment, so scientists monitor every batch. Fermentation produces a brew called liquid cream yeast, which is shipped out in tankers and trains to bakeries across the country. But some is destined for home use. Sheets of cream yeast are further dried on stainless steel drums and scraped to make cake yeast. Additionally, the cake yeast can be broken down into granules and slowly dried. This process, invented by Fleischmann's in the 1940s, causes the yeast to go dormant. This is called dry yeast and can last up to 2 years in this form, or until it's mixed with warm water and brought back to life to make bread rise. A combine harvests enough wheat for about 70 loaves of bread in 9 seconds.